Okay, so hopefully you have them in your back now. I just extracted the file. Okay, homework 4. You'll see, let's see, these files here that are highlighted. Okay, those are the ones you'll download. The one thing that I like to do before I continue is, because I know that when I open up Jupyter Lab, that I can't keep going back and forth, or like between projects or opening up different projects. It's just kind of a pain. So I like to move things into this directory, just copy and paste them in, things I'm going to need. You can do whatever you want, but it's just what I do. For here, it's going to be like 11 through 13, no 14, but 11 through 13. So if I come in here, 11.1, actually there isn't anything from 11.1 in there, but 11.2, I'll copy this from 11.2, and I'll paste it in there. Then I'll go back, and I'll go to 12, and I'll copy in solutions, just one set. I don't need the large ones. And then I'll come here to 13.1, I'll copy this one and paste it. Then 13.2, and just that one there. Okay, so all the solution files that you've downloaded, that's what I put in here: 11.2, 12, 13.1, 13.2. All right, and the reason I like that is because now they'll show up in here, and if I want to open them up to reference it, I can just pop it open and take a peek and get some code samples. All right, so go ahead and pause now and get Jupyter Lab running, and have your file, at least your homework 4 file ready, if not all the other ones, just in case. Okay, help you with copying and pasting. That's why I'm suggesting it. All right, so hopefully you did that and you're back now. I'm going to go ahead and minimize the folder so I get more viewing space here. Now let's go ahead and read the instructions and get through this. So complete the numbered items herein, execute the code, and answer the questions at the end. Turn in this file to Canvas. This is the only file I want for Canvas. Okay, if I go back to here, for instance, and homework 4, basically says that, right? So we're doing a couple things in here. We're going to read data from a data set, flatten it, analyze it using data analytic and supervised machine learning techniques. Just complete everything and turn in the IPYNB file. Okay, so your homework 4 file, you don't need anything else. You're not going to need this Word file anymore. Just instructions in case you're used to that. You know, some people are just used to downloading the instructions. I'll put that there for you. So only thing you need to turn in is this file here. That's it. Homework 4. That's it. Just one file. Nothing else. Okay. So it says no touching, so no touching, but you still got to run it. So make sure you run that first one. Good. Now here, if you need to, you can change your port number. Nothing else to change though, but I need to change my port number. So change the port number. All right. Now, no touching functions, but it's important that you understand them. So I just ran it. All right. It's important that you understand what's going on here. Okay, and what we're doing. So the first one is I have a function for train test split. I'm going to tell you to use this later on, but I'm going to say pass in train test split x, comma y, and then test size is just default is 0.3. And we're also using a random state of 31 that will keep us pretty close in terms of the responses. Now, in terms of train test split, we'll get the exact same output, but the way that some of these models work, we're not going to get the exact same output. Okay, and I know that because I ran this thing, I don't even know how many times last night, this morning, and it I got slightly different answers every single time, which is fine. I just wanted to see how close they were to each other. They're pretty close though. Okay, so I have a sense of the magnitude of what the responses should look like. But we're going to have a function here that does train test split. So I'm just going to call train test split, pass in x, pass in y. I could pass in, some other test size split, or you can just, or not pass anything in, and it'll use 0.3 as the default. But it will return x train, x test, y train, y test. Okay, so it returns those 4. Just like we've done before, except now it's just, I can call this function. This is not really that much different. It's just the reason why you kind of do this is if you're going to standardize it like a random state or something, or you can do something else with it, then you can do that. Now here we're going to have scale. Okay, and this applies the standard scalar. So if I just say scale and I pass in say x for instance, then it will say is b none, b is none, then it will just transform a. Okay, so there's one instance in here where we're not going to pass in x train, x test because we don't have a trainer test. We just have all of x that we're using. So we just call scale, just pass one value in, and it only returns one value back. If you pass in, say, x train, x test, then it scales x train, x test, and it returns the 2. So it'll return x train, x test, just like this here. Okay, just like that there. It'll return those. Execute model and execute grid search CV. So execute model, I can pass in, say, logistic regression, and then my x train, x test, y train, y test data, and it will fit the model. Okay, then it'll run the print report from the machine learning utility file. And so it just has everything here. It makes it a little easier for us to work with. I just say execute model, pass in 5 parameters, and it handles fitting everything and writing out the reports. Here's for grid search. So execute grid search CV, pass in the model, which could be logistic regression again, our parameter grid, our K, all of our training and testing data. And then it handles the model generation, number of folds, and here we have number of jobs is n-1. Some of these took a minute on my machine to run, like 70 seconds or so on my machine to run, and they might take several minutes to run on yours. Because when I say number of jobs -1, that means use all the cores on your machine, all the threads, and so mine has 36, and that thing just lit up like a Christmas tree last night when I was running it. It was like completely peaked. Every single thing was running, and it still took like 70 seconds to run these. So it might take several minutes, but n jobs equals -1. That means use all available cores that you can. And so it creates that, it fits it, it prints out the best parameters, then it prints the cross-validation results. So you just have to write one line of code, everything spits out for you. Now transform, this will transform your model. Okay, transform and filter will transform as well. So here we could pass in like linear discriminant analysis or something like that, and have it transform and fit with XY. Okay, like LDA. And here we could do like a PCA or SVM or something like that, where we can actually set a variance threshold and it'll return just the results that are required to meet that variance. Okay, so just a bunch of functions already written in here for you. Just minimize how much you have to write going forward. So that's run. Now let's move on down to 1A. It says no touching, okay? But you still got to be able to read through it and see what's going on. A lot of this stuff I've already given you, and a lot of this stuff you should be able to read by now and understand at least a little bit. So schemas, machine learning. Okay, the query we're running here is just the limited query, the exact same query that we used in is it 13.2? One of these might not have been here. State 12, 13.1 maybe. 13.1, yeah. So it's 13.1. It's this query here from 13.1, the limited query response. Okay, and that'll set data from there. And this here is slightly different. Okay, so this one here, we're using CPT as opposed to DX data. So here we're using, oh, that's not it. Oh yeah, IC10. We're using IC10. We're using the counters from 0. Okay, yeah, the DX table. Yeah, we're using the diseases table here in 13.1. And here instead of diseases, I am using the CPT table. Okay, so I'm using CPT. And I'm using patient, yep, okay, billing. So it's a CPT. The billing table is that weak entity, and then CPT is the dictionary. So I'm actually going to return the CPT codes here as opposed to the IDs. So back here in 13.1, I just used the DX table, which was just the weak entity, and it spit back the IDs, which made it very difficult for us to interpret because it's just some random ID. It wasn't an actual code. Here we get the actual CPT codes back. So when we generate the columns, they'll be the actual CPT codes. Next, we'll pivot that table. All right. So we're gonna have one. So index means the number of the row. Unique rows are going to be on the encounter, and then we're going to convert all the unique values into new columns, and then we're going to basically the value is going to be that, but we're going to take the length. So we're going to count the number of CPTs, and that's going to be our value, and we're going to fill NA 0 and then as type int, which is very similar to this. We did that, except we did it in multiple steps. We filtered a little bit. We're not going to do that, but here's that pivot result. Except here we're pivoting on ICD-10 CMIDs, counting those. Then we filled NA. Then we did as type. Then next we're going to merge. So you can see I'm just kind of going step by step down 13.1. Then we're going to merge. Okay, and here's that merge on encounter ID. And we're going to delete the CPT table because it's kind of big. Don't want that in memory as well. And so what's left over is just the data table. So I'm going to go ahead and run that so we can kind of see what's going on. We're just going to have one table left. And you can see here it has 29,607 rows, 640 columns. And these codes down here at the end, these are the actual CPT codes. And we can see the encounter information right here at the beginning. So encounter information followed by all the CPT data. All right. Now it's time to start writing code. So I give you some hints at the beginning, 13.1. Okay. To come back to 13.1, just kind of keep scrolling down, and what we're going to look for is something similar to this. So create column died. Okay. There's 13.1. Oh look, create column died. Generate dummies and clean. We're not going to generate any dummies or drop this. We're simply going to just create column died. So I'm just going to copy this. Copy the whole thing actually. Come here and just paste it. Because we're using the same table name. I try to make it as easy as possible. The same table names. Everything's going to be the same. Just execute it. There we go. Okay. So we created that column died. Next, I want to drop column discharge disposition code. So how we drop discharge disposition? Blah, right here. That's it. Okay. 13.1 again. Copy it. paste it, and you can run it. It'll drop that. Okay, so we can see 641, 640, one column less. Now I want to create dummies for race, Hispanic, gender, insurance code, transport code. We can find that right here in 13.1. Get dummies. All right, it's a lot of copy paste. Just want to get some practice. Just at least finding the right set of code, right? So here we have pd.get dummies, data, columns, and so on. Let's run that. Perfect. Now we need to write df to CSV. Come back to here, and you can see write df to CSV. Of course, it's going to be slightly different, okay, in terms of what we need. We can start with this, come back to here, and paste it, but it's going to be a different file name, and you probably want to rename this too. Okay, so you can see what the file name is. Copy paste that, and flatten encounter CPT or whatever. I don't know. However you want to put it, as long as it works. And run that. And check to make sure it's here. There it is. Just generated it. Okay. About 37 megs, 36, 37. Let me check. Yeah, 37.5 megs. That is our file. So that completes part 1. All right, so we're going to prepare for train and test. Again, back to 13.1. And let's see what we need. So remove all null values, stores new data frame D, and print COVID-like illness value counts. Okay, so how do we remove null values? You can always go in here and do Control F and say remove nulls. Let's see if it's in there. Nope. No, well, there you go. So how do we remove null values? Drop NA perhaps? Okay. Doesn't like nulls. All right, so there we go. Just rephrase it a little bit. So what we need to do is we need to get rid of the null values. We're going to start with data though. So data dot drop NA. It's a function. And now here we need to do, we need D dot, and then we need to do COVID-like illness value counts. Okay. So, oh, there it is. Exact same thing. Look at that. COVID-like illness value counts. Run that. All right. Now we're going to set X and Y. Do this manually. All right. And it's just like this stuff here. You can copy the X and Y. You can paste it. What we're basically saying is D.locate. We're looking for all the rows where the column name does not equal COVID-like illness. And here we're just selecting COVID-like illness. Printing out the value counts again. All right. There we go. That's the Y value counts, same as up here. So remember, we're using COVID-like illness as our Y. Now moving into oversampling. This could be 11.2. If we scroll around looking for oversample, let's see. There it is. So here's example of oversampling in 11.2. And then here we have an undersampler, and here we have an oversampler. All right. So I want you to go ahead and run the oversampler. Go ahead and write the code to do it. But here we're going to do from. Yeah, it's going to be from something. We're going to just overwrite X and Y again. Okay. So like here, we see X over, Y over. We're not worrying about over and under and then X and Y and comparing it. We're just going to keep overwriting X and Y because we don't want to have a whole bunch of copies of X and Y running around. It just fills up the memory. So we're just going to, oversample X, Y, and then store them as X, Y. So go ahead and do that now. I'm going to pause, run it, so we can keep going. Okay, so I ran it, and we can see it completely oversampled. It didn't reduce the zeros at all, the non-COVID. It just increased the COVID. Okay, so 15,138, 15,138. Cool. Now we're going to do train test split. It tells you right here exactly what you're going to run. Train test split. Super simple. Here it tells you exactly what you're going to run. Okay, so run it. I'm not going to copy and paste it. I want you to do something. Okay, so go ahead and do that. I'm going to run it inside and come back. All right, I ran it. When I undo it, it just removes those marks, but I did run those. Okay, and that is it for number 2. On to part 3. Classification experiments. So feature preserving. We're going to run logistic regression, grid search CV. Not logistic regression CV, but grid search. All right. So here we have to import logistic regression, and call execute grid search with parameters, logistic regression. This is basically the parameters you need to pass in. Okay, like literally just like copy paste. So you need to import logistic regression. Let's see. Here's classification exercises in 12. And where's logistic regression? Oh, here we go. Here's grid search CV with logistic regression. So you can kind of see the setup a little bit here, except I have my own function that we're running. Okay. So here, where am I? I'm in 1B5, week 12. You can kind of get a sense of that. So where's the import? Not there. Not yet. That's CV. Standard scalar. Not yet. Keep going up, 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 up. There we go. And so there it is. There's the logistic regression import command. So you need to add that in there. And then once you've done that, we need to add in execute grid search CV and just run it, right? So execute grid search CV. It's not going to return any value. And then we need to put something inside the parentheses, and it's just all this. All that goes in the parentheses, and then you can run it. I'm going to go ahead and pause and execute. All right, so it's running right now. This might take a moment. While this is running, and it moves off to the side, what I want is I'm going to want to start writing this information down. Okay. You might want to pull up a spreadsheet or a text file or something. I'm just going to go ahead and add a spreadsheet to this. I haven't tried that one yet. We'll just do output or whatever, doesn't matter. And pull it up. Still going. And what I'm going to want to do here is kind of put down the experiment, logistic regression, grid search, CV or something, doesn't matter, whatever it is. Okay. And I'm going to want to start. There we go. So here we have our parameters, 100. So this ran all these different combinations 5 times. Okay, so it has a train test split. Okay, well, I did train test split already of 30. Here we're doing 5 cross-fold validation. So it's chopping everything into 5 pieces and running that. So it's doing 4 pieces, leaving 1. So it's training on 4, testing on 1, and it's training on all combinations of 4 and testing on the remaining 1 each time. And we're doing L1 100 liblinear, L1 100 saga, L1 250 liblinear, L1 250 saga, and then L2 100 liblinear, and so on. Okay, all the possible combinations of what I'm listing here. And we can see that 100 iterations, that was the best, that was the default. L2 was the best, that was the default. And liblinear is the best, and the default here didn't actually work unless it was multi-class classification. So, and this changes from time to time. Like I ran this a bunch of times last night, early this morning, and it was like 100, 250, 100, 250. If it was 250, it usually pick like L1 also. It's kind of weird. And saga as well. So we kind of went back and forth, went around, but they were all really, really close to each other. So now what we have is we see, let me just pull that up, in the value. So here I'm going to put the accuracy, 94.07. No, 0.07, okay? And then I'll just put in basically the numbers for our confusion matrix. And I'll put the confusion matrix values in, 4299. Then the rock curve value. And then I'll put my time in too. So this took me 73 seconds. Okay. And the reason I'm doing this is because at the very end, we're going to need to compare algorithms. So I just want to start writing everything down here just so I have it, make it nice and easy. Okay. So there's that, those results. Now, what do we think of these results? They okay? They good? They bad? What do you think? Means a decent baseline. I mean, it's still 94% accurate. It's not bad. That's pretty good. But let's see what we can do to improve. If we can improve, we can try. So another thing we can try is KNN with grid search. So we're going to try 2 to 20 neighbors, 5 here. And I kind of tuned these because some of these have run for like 20, 30 minutes on my machine. And I was like, okay, well, that's going to take like, forever on your machines. It doesn't crash. So I minimized K and I shrunk down these ranges and so on just so that it would work on your machine. Hopefully it'll work. But all we need to do here is we'll need to import that there. Okay, neighbors classifier. Which, let's see, that's probably going to be in 12 also. I don't know. Oh, there it is. K nearest neighbor classifier. All right. So we need to import that. And basically, we just need this, the execute grid search, whatever you did, we'll need that for this as well. The only difference is that will just pass in K nearest neighbor classifier. So here's the contents. All right. So go ahead, fill that in and run it. Okay, so I'm running mine now. Yesterday, this took me 26.6 seconds. Since I'm recording, though, it's a lot more resource utilization than yesterday, so it might be a little slower. But I'll get ready for it. KNN grid search CV. And we have a 93.76. Interesting, because when I ran this yesterday, these numbers were reversed. Cool. So whenever you run it, you get slightly different numbers. So 0, 0.92, 0.96, 0.94, 1, 0.96, 0.91, 0.94. And then let's look at the confusion matrix. 4, 3, 8, 2, 1, 7, 7, 390. Ouch. 4, 1, 3, 4. So when I look at these, this kind of happened yesterday as well, where it decreased. What do we see here, right? You know, I'm looking at the falses, right? It's a false positive up here. It's a false negative down here. So our false positives definitely got better with KNN. Problem is our false negatives got a lot worse. Okay, this is negligible difference in accuracy when you think about it. I mean, if you run it 20 times and you probably get something close. They're probably both around 94. When I ran this yesterday, I got a 93, 94. The last time I ran it, and this one here I got a 90. What is it? 94.08. So they're both around 94. Okay, let's look at the rock. 0.96 and time 27.9 seconds. Oh, yeah. Okay, 73. Look at the difference. I mean, 73 seconds, 23 seconds. That's a huge difference. But also 98 versus 96, so we're just not nearly as accurate. Okay, and we can see here that these are all 94s. Now, yeah, we have 96s, but we also got 92 and a 91. Okay, it's just showing us that we're not doing very well, particularly in this arena here. Okay, we actually got a lot better in terms of identifying our true negatives. True negatives. And we got a lot better at identifying false positives. Well, minimizing false positives, I should say, which basically means we're better at identifying true negatives. Problem is we're not very good in terms of negatives in general because we have a lot of false negatives, okay, as opposed to true positives. So the question then becomes, what do you think? I mean, this is faster, okay? I mean, yeah, 73 seconds versus 27.9 seconds. What do you do? No one really cares. But imagine this was on the full data set where this one here is taking, you know, an hour, and this one here is taking 25 minutes, right? 20 minutes. Yeah, about 20 minute difference. Yeah, 25 minutes. That could be a huge difference when this is on larger data sets. Plus, that assumes this scales linearly, and it might not. Okay, but just things to consider. All right, what's next? Oh, an MLP, multi-layer perceptron. Let's go back to 12 and see how we did with multi-layer perceptrons. Remember, it's kind of like it's like a neural network, but with one hidden node, just one. This is input. It is an input, a set of inputs, hidden layers, or hidden layer singular with multiple nodes, and then you have the output layer. So it's 3 layers: input, hidden, output layer. Most deep learning will have like input, a couple hundred different hidden layers, and then one output layer. So here we go. Here's our MLP. And so what we need to do here is we'll need to import our MLP and then feed that into execute model. Okay. Not execute grid search CV. I tried this. I let it run for like an hour on my machine. And we're talking like an hour, 36 core, well, 18 cores with dual threads. I mean, this thing was pegged at 100% for an hour running last night, and it didn't finish. Okay, it's just way too expensive to run grid search on this. So I was like, well, you know, maybe we just run a base model without even configuring it, just out of the box and see how it does. If it does well, then we don't even need to worry about tuning it. Let's just run it out of the box and see what happens. Okay, just give it something to do. You know, normally, if I'm really running this, I would. You know, well, honestly, I'd probably find something that's GPU enabled for this because it's so slow. But I would just let it run. You know, I just continue to let this thing run, and I would shut down anything on my machine I didn't absolutely need to give it more processing availability. But for this, we're just going to run it as a base. So the big thing here is execute model, which is different. You see this here? That's what you're going to pass in. You know, there's not a param grid and there's not a K because we're not doing that. It just took too long, too expensive to bother. So import your MLP classifier and then run execute model with these parameters. Okay, so it's running now. And let's see, this took me 95 seconds yesterday. So with the recording going, it's probably gonna take about 100 seconds to run. All right, so that's going. Let's go ahead and get all set up for this. MLP, multi-layer perceptron. I mean, it depends on how you want to write this down. This is kind of long. Maybe I'll clean these up a little bit. logistic regression, grid search, like that. Because I can just copy and paste these into my results later on. That might save me some time of having to format things later. At the very bottom, I have questions. I want you to rank order certain things and answer a final question. So it helps just have this here because I can just copy this in and then just whatever the time is or whatever the values I'm looking at, whatever I'm evaluating. Okay, still going. Already, make sure you save this too. I'm not going to save it because I already have it saved in a different document, but I mean, just save it. All right. Now remember, because we have time it here, whatever we build in here will not exist outside of it. So when we do this one here, the principal component analysis next, x scaled, I need x scaled because I have x. I can't take x, overwrite x because it's outside and inside. So whatever's inside here will not be accessible to any other cell. Time it basically like creates its own virtual environment that's separate memory-wise from everything else. It brings in what it needs to from the outside, external memory, but it does not write back to the full system memory. It keeps everything isolated. So whatever's in here can't be used later on, which is why everything is in one cell. I couldn't just do scale here and then results. Not if I needed to time it, because if I needed to time it, then it wouldn't exist outside. There we go. 1 minute 48 seconds. Okay, definitely took a lot longer, but look at that. Woo woo. So we want the testing accuracy for this. We get 2 scores back. Testing accuracy, 95.85%. Look at that. That is the best by far, and it's just the base one. Just the base. Let's take a look at this. I got 0.95, 0.97, 0.96. Interesting is this is 0.97. Oops, sorry, 0.97. Oh, come on. 0.95, 0.96. These are exactly opposite from yesterday when I ran it. This was 97, this was 95. Okay, but they're still really good, obviously. 4406, 153, and 224, 4300. And these are swapped. This was really small yesterday, and this was a little bigger. It's interesting. Now I kind of look here. So false negatives, 224, 279. This took a while, though. Okay. What's my rock? 99, that's good. And this took 108 seconds. All right. Okay. Now that was the feature preserving one. If we wanted to look at the results, we could print the results out and actually see which columns had an effect on this. Okay, a little harder for MLPs, but you know, let's not go there right now. But these are still feature preserving. We didn't do anything to manipulate the features. Now, what we're going to do here is we're going to switch to non-feature preserving, which would be your principal component analysis, which would be support vector machines, SVM, or SVC, support vector classifier, as you know what we'd see in here. We're not doing SVM here, and then and also linear discriminant analysis, LDA. Remember, LDA produces the same number of columns as classifiers, so it's just there's one, so it just produces one column. All right, so we're about done. Okay, we're almost done. Okay, the point was just to kind of get you to do this, and then mostly spend some time analyzing it and writing stuff at the end. Okay, so we're going to do PCA next. This is PCA with MLP. Because we're going to run principal component analysis, and when we're done, we still need to feed it into something. So I'm going to feed it into MLP. Okay. Why? I mean, because MLP was best, but yeah, it was best. But it had the worst time. But let's see if we can improve upon the time. If you want me, normally you would switch through. I actually had you running multiple of these, like linear. I had linear regression and then MLP. The problem was you have to run all this stuff twice because all this stuff here would have to be run twice. You have one cell for logistic regression, another cell for MLP because it wouldn't transfer over in order to get the timing right. And so I said, yeah, forget it. We'll just do one at a time. So here we're going to use PCA. And where's PCA? Well, that's going to be under dimensionality reduction. Because that's what it is, right? And it's toward the bottom. And see, we're still in feature selection, sequential, keep going, dimensionality reduction, principal component analysis. So here is pretty much where we are, what we're going to use. Now, I already have that function that does this for us, don't I? Right? Go back to here, homework, and I scroll back up. That's why I put this here, this transform and filter. So we could actually just do it all in one step and not have to worry about writing the iterators ourselves. I can just call a very simple function. I need to import PCA, which I left. That was dumb. Oh, well, there you go. Congratulations, I left it. I missed it. Okay, I left. Then we're going to transform. We're literally going to run this transform command. Okay, just so you can see it. We're going to run that transform command. And we're going to store that as X results. Then we're going to print X results. Okay, now after that, we're going to do a train test split. Now remember, it's going to return this value here, so that's like everything over here is that. And we saw that a lot earlier in terms of what's returned. Okay. And right here, right? That's what we're going to run, basically. You can copy and paste that, but we're still going to tweak it a little bit. So we're going to run that. The difference is we're going to pass in X results. Okay, we're not going to pass in Y, we're going to pass in X results, which X results should really be like X PCA or something like that, but we're going to use X results. Okay, so it's just the results of the PCA analysis. That's going to give us new train test split based upon the new set of X that we have after principal component analysis. Next thing we're going to do is we are going to import the MLP classifier. Why would we import it again? Because again, up here, when we imported it right here, the one above when we imported it, it's under time it, so it doesn't exist outside of this. So we're going to have to import it again. So import that again, and then we'll just literally run the same thing again. Okay, so you have the execute command here, the same. So basically, these two lines here are the exact same. All right, we're changing X results affects just the train test split. Everything else I left as the same values, just in case. Like if you're not doing time it, then we can write a function that does a lot of this stuff for us. We can feed in something in the middle and go from there, just to kind of minimize the amount of code. Because this is really the exact same thing here, right? That's why this is worth 0 points. The first one, third and fourth, are worth 0 points because they're the exact same thing as up here. Only thing we're changing is this here. That's it. Okay. All right. So go ahead and complete this and run it. Okay, now I ran it. Okay, and what we're seeing here, here's the output. It's not done yet. What we're seeing, if you look at the function, transform and filter, print X results, right? So the result from transform and filter, that's going to be our X results right here. And we're printing those out. So that's what we saw here is X results. So it actually chose 99 columns, and it picked, well, actually, I chose 100 columns, 0 to 99, and we told it to pick at most 100 columns. So it didn't even filter anything, right? So we passed in, I believe, 652 or something. We passed in over 600 columns. We said, just pick 100, and from the 100, just make sure we get this much variance coverage. It's like, I'm sorry, I'll take 100, and I still can't get to that level of variance, which is kind of interesting, to be honest. When I scaled these, when I did not scale these, before they were scaled, when I ran it, it selected one attribute. That was it. There was one attribute that was so big, so different, it just used that one attribute. And it wasn't very accurate. So I switched to a scaled value, and then it got very different. So let's see. So that's using 100, okay, 100 columns. And here's our accuracy. So, like here we had, I wrote down 98.85. Oh, good grief. Sorry. 95.85, sorry about that. 95.85. I read the 98 and the 85. I'm sorry. So 95.85, which is still pretty good. I'm sorry about that. You're probably like, yeah, you wrote it down wrong. Yep, you're right. Totally right. Totally did write it down wrong. I'm sorry about that. And here we have what? 95.74. 0, 0.96, 0.96. They're all the same, aren't they? Okay. Let's look at the confusion matrix. 455, 204, 183, 4641. Definitely got better with false negatives. 25.5 seconds. Interesting, right? So just MLP by itself took 108 seconds. But when we performed principal component analysis first, it only took 25.5 seconds. It took a quarter of the time. It took a quarter of the time to get hardly at all different answer. And let's see, it's a little worse. Quite a bit worse, almost 50, 51 in terms of false positives, but a little better here, 41 in terms of false negatives. Okay. I'll probably go back, and when I see that I made a mistake up here, I'll try to put in a pop-up box at the bottom. You think it's easy, but it's actually not all that easy. All right, now we're going to the last one, linear discriminant analysis. Okay, only 2 is different from PCA. We're just going to do the same thing as before. So you can copy and paste everything you did up here, except we're going to use linear discriminant analysis instead. Okay, and we can find that under 13.2 as well. When we scroll down here past SVM into LDA. And here's all the stuff for LDA, okay? All the stuff. All right. We're also going to do transform here instead of transform and filter. Just transform, not transform and filter, just transform. Reason being, because transform and filter, we have more than one column coming back. With this here for LDA, we just have one column. Okay, we're not going to filter those out. Everything else is the same. So go ahead and run that. Okay, that's running, and it should be done in a matter of seconds. Okay, it picked one value, and we're Already done. 4.73 seconds. So how did we do? We did LDA with MLP. 93.99. Oh, come on. Oh, good grief. I'm having a bad day. There you go. 0, 0.9, 0.93, 0.96, 0.94, 0.94, 51. Okay. 4357, 202, 344. Check out my rock curve. 98. Oh, I didn't write the rock curve down here, up here, did I? Rock number for the previous was 99. Sorry about that. See, when I talk about it, sometimes I miss things. I'm sorry. 98 and 4.73 seconds. 4.73. So I'm going to put 4.7 seconds. Okay. All right, that's it. Okay, that is all the code that you need to write and run. Now we just need to answer the questions. Let's keep that over there. All right. So everything fits. And the question. So answer the questions below in each cell. So just write it in here. So here's the question. Number 1. Rank the experiments by test accuracy, most to least accurate. All right. So the easy thing to do is just kind of copy. Ooh. Going to copy these. I don't know where it's going to go. I'll just paste it below. And then my accuracy. Okay, I might put a % at the end or something. And so we'll do the next one. Okay. And then just keep going. Okay, do all of them. And then you're going to rank them, okay, from most accurate to least accurate. So larger to smaller. So you can remove this, of course. And that'll be number 1. So literally just put the list in there. Most accurate to least accurate. Okay. Now here you do the same thing, except it's going to be fastest to slowest. Fastest in time in seconds. So put the first one. So the fastest was easily the LDA, right? So you could do LDA MLP or something like that. And you put like 4.7 seconds. That's number 1. The longest one, slowest one was MLP, right? Right here, 108 seconds. Which is MLP. So last would be the MLP, just straight MLP at 108 seconds. You fill in the middle. Now here, rank the experiments by the false negatives. Fewest false negatives to most false negatives. So the fewest, I don't even know, right? That's all everything down. 279, that's better than that. Oh, 224, that's the best so far. 224, 183. Okay, so PCA MLP 183. And then MLP, sorry. MLP is 224, PCA MLP 183. 344. So in these experiments here, PCA MLP is the fastest. Interesting, because when I ran it yesterday, this was the best. Not fastest, excuse me. This was the best, because these numbers were reversed yesterday. They were reversed. Interesting. But so yeah, PCA MLP is going to be it's going to have the lowest number. Then the highest, what, 344, 390. Woo. KNN. Okay, KNN is the highest. That's 3. Now 4 is, which is the best result overall, and justify it. So you're just going to write down which one's the best, okay? Now your answer is going to be slightly different for me because you could have different results. Like I said, I got different results for myself yesterday. So that's why I'm going to look at your answers. Okay, so make sure when you turn this in, you turn it in completed. That's why I want this sheet, because all the results are here. I get the code and I get your results. I don't have to run it again, okay? And so if I run it again, I'm going to get something different. So just leave it, run it, and just turn this in. Run it, save it, turn it in with the results there. Okay? So after you're done with this, like literally, you can, it's like it's saved. Just turn in that file, just like that. Just turn it in. With everything in there. Just turn it in so I can see it all. Alright? I shouldn't have to run any of this code again. It's just there. I'm just going to come down here. I'm going to kind of look through your results, see what you got. I'm going to look at questions. I'm just going to read through your answers. This one here is the best one overall. Why did you pick it? Okay? If you think that, okay, it's 9574, 9585. So MLP, if you think MLP is better because it has the better accuracy, okay. If you're going to go off accuracy, that's one answer. If you're going to go off of time, then that's going to be a different answer. If you're going to go off of false negatives, that's a different answer. If you want to use something else that's not part of these three questions, if you want to use false positives, if you want to look at the different the metrics here that were presented, okay, so your precision, your recall, your F-score, your F1 score, excuse me. All right, if you want to go off of those, you can. Just explain it. If you want to go off the rock, go ahead, all right? If you want to use a conjunction of these, a combination of these, just go ahead and do that. So whatever it is, whatever you think is the best, based upon your results, that's what you're going to write up. And tell me why. Don't just say, you know, LR grid search CV is the best. That's not going to cut it for me, okay? I need a justification. This should be, a paragraph. Okay, I mean, at least 2, 3, 4 sentences. Okay, okay, but just justify why did you pick this one over other models. Okay, it's probably gonna be a multi-dimensional answer. Well, it's better here. It's not the best here, but it's good enough here. Blah, 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 and so on. All right, so that's it. That's all I want for this assignment. Not too difficult. Hopefully you can get through it really fast. I just wanted you to spend some time practicing it, but then also to go through and to try to communicate the results and which model you think is the best and why. All right, so that's it. If you have any questions, let me know.